Have you ever wondered why your morning coffee sometimes tastes like liquid gold, and other times like bitter disappointment? Brewing coffee isn't just a morning ritual, it's a fascinating blend of science, art, and precision. Behind every delicious cup lies a series of invisible yet powerful theories, from the chemistry of extraction to the physics of pressure, and even the quiet role of water's mineral makeup. Whether you're a home barista chasing cafe-level quality or a coffee lover curious about what makes your brew tick, understanding the deeper mechanics of coffee brewing will forever change how you see and taste that simple cup. Let's explore the hidden science that transforms beans and water into one of the world's most beloved beverages. Coffee isn't just a beverage, it's a carefully engineered experience. From the first grind to the final sip, the way we brew coffee is shaped by a range of scientific principles that govern flavor, aroma, and texture. Yet most people never realize how complex their cup truly is. Why does one brew taste vibrant and balanced, while another is flat or bitter, even using the same beans? The answer lies in understanding the variables at play: extraction, temperature, grind size, water chemistry, pressure, and time. Each one of these elements forms the backbone of a coffee brewing theory, frameworks developed through observation, experimentation, and refinement. This guide will walk you through these interconnected theories and help demystify the science behind exceptional coffee. Whether you're an aspiring barista or a curious enthusiast, knowing these fundamentals will empower you to brew with both intention and consistency. 1. Extraction theory. The foundation of brewing. The essence of coffee brewing lies in the principle of extraction, the process of pulling soluble compounds from ground coffee into water. This is a complex interaction influenced by time, temperature, grind size, and water chemistry. Extraction occurs in stages. Initially, bright and acidic compounds dissolve, followed by sweet, aromatic compounds, and finally, bitter compounds like caffeine and chlorogenic acids. The goal is to reach a balanced extraction where the acidity, sweetness, and bitterness complement each other. Industry professionals often aim for an extraction yield between 18% and 22%, which is considered the ideal range for flavor harmony. Under-extraction leads to sour, weak coffee, while over-extraction results in bitterness and dryness. Mastering this balance is the cornerstone of good brewing. 2. TDS and extraction yield theory. Measuring success. To measure how effectively coffee is brewed, two metrics are often used: total dissolved solids, TDS, and extraction yield. TDS refers to the percentage of dissolved coffee solids in the final beverage and is measured with a refractometer. Extraction yield is a calculation that tells you what percentage of the coffee's original mass has been transferred to the cup. The formula is TDS times brewed coffee mass divided by dry coffee mass. These measurements are typically visualized using the coffee brewing control chart, a graph that shows how different brews fall into categories like under-extracted, over-extracted, or optimally extracted. Baristas use this chart to calibrate recipes and ensure consistency. Understanding and measuring these variables scientifically bridges the gap between guesswork and mastery. 3. Temperature theory. The heat behind the brew. Water temperature plays a critical role in the brewing process, as it directly affects which compounds are extracted from the coffee grounds. The optimal temperature range for brewing is generally between 90 degrees Celsius and 96 degrees Celsius, 195 to 205 degrees Fahrenheit. Water that is too cool fails to dissolve enough of the flavor compounds, leading to under-extracted, sour coffee. On the other hand, water above 96 degrees Celsius can cause over-extraction, drawing out bitter and harsh flavors. Different brewing methods react differently to temperature changes. Cold brew, for instance, uses much lower temperatures but compensates with longer steeping times. Even slight variations in temperature can significantly change the flavor profile, making thermal control one of the most important elements in achieving consistent quality. 4. Grind size theory. The power of the particle grind size determines the surface area of coffee exposed to water and plays a pivotal role in extraction speed and uniformity. Finer grinds expose more surface area, leading to faster extraction, while coarser grinds slow the process. The grind must be matched to the brewing method. Espresso, which brews quickly under high pressure, requires a very fine grind. Pour over and AeroPress use a medium to fine grind, while French press and cold brew call for a coarser grind to avoid over-extraction during their longer brew times. An inconsistent grind, often a result of poor quality grinders, can lead to channeling, where water flows unevenly through the coffee bed, causing some grounds to be over-extracted and others under-extracted. This leads to an unbalanced cup with muddled flavors. 5. Brew time and contact time. Timing is everything. Brew time, or contact time, refers to the duration that water interacts with coffee grounds. Different brewing methods require different contact times for optimal extraction. For example, espresso uses high pressure to extract coffee in about 25 to 30 seconds. Pour-over methods typically take 2.5 to 4 minutes, while French press immersion takes around 4 minutes before the plunger is pressed. Cold brew is a slow method, often requiring 12 to 24 hours due to the low temperature of the water. The correct contact time allows for balanced extraction of acids, sugars, and bitters. If water passes through the grounds too quickly or too slowly, the resulting brew can be either weak and sour or bitter and dry. Perfecting contact time is essential to tailoring the brew to the desired flavor profile. 6. Pressure theory. The physics of espresso pressure is what distinguishes espresso from all other brewing methods. Using about 9 bars of pressure, espresso machines force hot water through a compacted puck of finely ground coffee in less than 30 seconds. This intense pressure allows for quick extraction of a high concentration of soluble compounds and oils, resulting in a rich, full-bodied shot. It also creates crema, the golden foam on top of espresso made from emulsified oils and carbon dioxide microbubbles. Crema is both a visual cue of freshness and a flavor enhancer. Proper tamping, grind consistency, and water temperature all affect how pressure acts on the puck. Inconsistent pressure can lead to channeling or incomplete extraction, affecting both taste and crema quality. 7. Turbulence and agitation theory. Stirring up flavor. Agitation refers to the movement of water through and around the coffee grounds during brewing. In manual methods like pour over or AeroPress, the way you pour water, whether in circular motions, pulses, or in a continuous stream, affects how evenly the grounds are saturated. Gentle agitation helps ensure even extraction, while excessive turbulence can cause over-extraction and bitterness. Stirring during bloom or after adding water can break clumps and improve flow, but if done too aggressively, it may disrupt the coffee bed. In immersion methods, like French press or cupping, stirring distributes grounds and accelerates extraction. Understanding how to use agitation correctly adds another layer of control over the brewing process. 8. Water chemistry theory. The hidden ingredient water is not just a neutral solvent, it's the most overlooked variable in coffee brewing. Composed of minerals like calcium, magnesium, and bicarbonate, water can dramatically influence flavor extraction. Hard water, which is high in minerals, may bind to certain flavor compounds and suppress acidity or aromatics. Soft water, lacking essential minerals, may under-extract, resulting in flat or sour brews. The Specialty Coffee Association recommends water with around 150 parts per million, ppm, total hardness and a near-neutral pH, around 7.0 to 8.0, for optimal brewing. Many cafes use water filtration or remineralization systems to create ideal water profiles. Without proper water chemistry, even the best beans and equipment will yield subpar results. 9. Maillard reaction and roasting theory. Building the flavor of coffee begins not in the brew but in the roast. The Maillard reaction, a form of non-enzymatic browning, occurs during roasting when amino acids and sugars react to form hundreds of aromatic compounds. As roasting continues, caramelization breaks down sugars and develops body and sweetness, while the coffee bean's internal structure transforms. Light roasts preserve origin flavors and acidity, while dark roasts emphasize roast character, body, and bitterness. Roasting also influences solubility. Darker beans extract more quickly due to their more porous structure. Brewing should always consider the roast profile, adjusting grind size, water temperature, and extraction time to bring out the best characteristics of the roast level. 10. Crema formation theory. A mark of espresso quality crema is the creamy, golden brown foam that sits atop a freshly brewed espresso shot. It forms when carbon dioxide gas, trapped in roasted coffee, is released under high pressure during extraction. This gas emulsifies with coffee oils and floats to the surface in a layer of microbubbles. Crema is considered a hallmark of freshness and quality, but it is not just decorative. It contributes to the mouthfeel and aroma of espresso. However, crema quality can vary based on roast freshness, grind size, water temperature, and pressure. Stale coffee or improper technique can produce thin or non-existent crema, which often indicates a lackluster shot. 11. Golden ratio theory. The blueprint of balanced the coffee-to-water ratio is the most fundamental brewing guideline, known as the golden ratio. Most professionals recommend a ratio between 1:15 and 1:18, meaning 1 gram of coffee for every 15 to 18 grams of water. This ratio helps control the brew's strength and flavor intensity. For a stronger brew, such as a cold brew concentrate, a 1:12 ratio may be used. For a more diluted profile, as with some drip coffee preferences, a 1:20 ratio might be appropriate. The golden ratio serves as a starting point for recipe development and can be fine-tuned according to roast level, brewing method, and personal taste. 12. Blooming theory. Let the coffee breathe. Freshly roasted coffee beans release carbon dioxide gas trapped during the roasting process. When hot water is first poured over the grounds, especially in pour-over or aeropress methods, the gas escapes rapidly, a phase known as the bloom. Allowing coffee to bloom for 30 to 45 seconds ensures that carbon dioxide doesn't disrupt the brewing process by forming air pockets that repel water and cause uneven extraction. Blooming is particularly important for fresh beans and plays a crucial role in the clarity and balance of the final brew. 13. Coffee freshness and degassing theory. The clock is ticking. Freshness is vital to coffee flavor. After roasting, coffee goes through a degassing phase in which it releases carbon dioxide. While some gas is necessary for crema in espresso, too much carbon dioxide can cause turbulence and uneven extraction. Coffee is typically at its peak flavor between 3 to 14 days post-roast. Ground coffee loses freshness much faster due to increased surface area and exposure to oxygen. Oxidation leads to flavor degradation, staleness, and bitterness. For best results, grind just before brewing and store beans in airtight containers away from light, heat, and moisture. 14. Thermal stability theory. Consistent heat, consistent brewing equipment should maintain stable temperature to avoid swings that disrupt extraction. Materials like ceramic, metal, or double-walled glass retain heat better than plastic. Preheating your dripper, cup, or French press can prevent heat loss that leads to under-extraction. In espresso, machines must maintain boiler temperature with precision. Fluctuations can ruin shot consistency. In manual brews, thermal stability ensures that water extracts coffee compounds evenly from start to finish. Controlling heat from kettle to cup is a subtle but powerful way to improve brew quality. The perfect cup of coffee is no accident, it's the product of science applied with care. Behind every satisfying sip is a balance of variables that work in harmony: water meeting coffee, time dancing with temperature, and flavor emerging through deliberate extraction. Once you understand the theories behind coffee brewing, you begin to see each step, grinding, pouring, blooming, not as routine, but as purposeful decisions. Mastering these concepts doesn't require a lab coat or fancy gear, just curiosity, practice, and a willingness to experiment. So next time you brew, pause and consider the unseen forces at work in your cup. Because the more you understand the science, the closer you come to consistently creating the magic that is truly great coffee.